class. Today we're going over Chapter 13, Voting and Apportionment. Looking at 13.3, the Apportionment Methods. So our objectives today are to find standard divisors and standard quotas, understand the apportionment problem, use Hamilton's method, understand the quota rule, use Jefferson's method, use Adams' method, and use Webster's method. So let's look at standard divisors and standard quotas. The definition of standard divisor is as follows. The standard divisor is found by dividing the total population under consideration by the number of items to be allocated, so that our standard divisor equals the total population divided by the number of allocated items. The standard quota for a particular group is found by dividing that group's population by the standard divisor. Our standard quota equals the population of a particular group divided by the standard divisor. So let's look at example 1, finding standard quotas. The Republic of Margaritaville is composed of 4 states, A, B, C, and D. The table of each state's population in thousands is given. Find the standard quotas for the states. So we have state A, B, C, and D in the total. We have a population of 275, 383, 465, 767, and 1,890 respectively for each of those states in the total. The standard divisor, recall, is a total population divided by the number of allocated items. Now the total population we can see directly in our chart here. Okay, so directly in our chart here we see that our total population is 1,890. Now our number of allocated items here for this example will be 30, and the problem just gives you that. Okay, so you don't have to calculate that or come up with that anywhere. Not yet, at least. Now, if we do look what this standard divisor comes out to be, the 1,890 divided by 30 gives us a standard divisor of 63 that we will use. The standard quotas are obtained by dividing each of the state's population by the standard divisor. So next we will look at the standard quotas. Okay, so we're basically going to calculate the standard quotas for each one of these states so we can fill this chart back in, and we'll do them one by one on the next page. So the standard quota for state A is the population of state A, which is 275, directly from the chart, right? And we're going to divide that by the standard divisor, the 63 that we calculated. So 275 divided by 63 gives us a 4.37. Now we'll look at the standard quota for state B. State B was 383. We divide that by the 63, we see 6.08. We look at the standard quota for state C. We've got 465 divided by 63. That gives us a 7.38. And we look at the standard quota for state D. Remember, state D had 767. We divide that by 63, and we see 12.17. So we now have the standard quotas for each state. Okay, so we can fill the chart back in, and that's what we've done here. So, got the chart filled back in. Obviously, the standard quota overall is 30 here. So if you did 1,890 divided by 63, you would get 30. Or if you added them all up, you would obviously get 30 as well. So it says, notice that the sum of all the standard quotas is 30. The total number of seats in the Congress. Okay. Now, here's the apportionment problem. The standard quotas represent each state's exact fair share of the 30 seats for the Congress of Margaritaville. Can state A have 4.37 seats in Congress? Now, state A cannot have 4.37 seats in Congress because you can't have a 0.37 of a person, okay, or of a seat in this case. The apportionment problem is to determine a method of rounding standard quota into whole numbers so that the sum of the numbers is the total number of allocated items. Can we round standard quotas up or down to the nearest whole number and solve this problem? So let's look at the lower quota versus the upper quota. The lower quota is the standard quota rounded down to the nearest whole number, while the upper quota is the standard quota rounded up to the nearest whole number. Now, here's the apportionment problem for Margaritaville. Okay, we see our original part of our chart here at the top, the state population and standard quota. If we look at the lower quota versus the upper quota, what the lower quota is going to do is round each of these numbers down. So if we look at state A here, it's going to round this 4.37 down to 4. It's going to round the 6.08 down to 6. It's going to round the 7.38 down to 7. And it's going to round the 12.17 down to 12. And if we add these together, 4 plus 6 is 10, plus 7 is 17, plus 12 is 29. We got a problem here because now we're completely missing a seat, right? It's supposed to fill up and have 30 seats, but now if we add the lower quotas together, we don't get 30 seats. We have a seat empty. We can't have that. The upper quota means we round all of them up. So we round 4.37 up to 5. We round 6.08 up to 7. We round 7.38 up to 8. We round 12.17 up to 13. And when we do that and total those together, 5 plus 7 plus 8 plus 13 gives us 33. And that's no good because the total is supposed to be 30 because we only have 30 seats in Congress and we can't have 3 extra seats. Okay? So there are 4 different apportionment methods called Hamilton's method, Jefferson's method, Adams' method, and Webster's method that we can use to round appropriately so that we wind up with the exact total we're supposed to. Because if we just round down or round up, we might not necessarily get the exact total that we are supposed to get. We could wind up a little below or a little above, and neither of those is good if you need exactly a specific number. So let's look at each of these methods, starting with Hamilton's method. We want to calculate the group standard quota. We want to round each standard quota down to the nearest whole number, thereby finding the lower quota. Initially, give each group its lower quota, and then give the surplus items one at a time to the groups with the largest decimal parts until there are no more surplus items. That's Hamilton's method. So let's look at it. We're going to keep the Margaritaville problem. Consider the lower quotas for the Margaritaville problem. We have a surplus of 1 seat, which means we need to fill 1 seat. And this is the exact same chart that we just saw back here, but we're only looking at the lower quota so that we can follow the 3-step Hamilton method. Now, the surplus seat is supposed to go to the state with the greatest decimal part. The greatest decimal part is 0.38 for state C. So if we look at state C here, state C has the greatest decimal part. Okay, so state A has 0.37, state B has 0.08, state C has 0.38, and state D has 0.17. State C has the biggest decimal point of all of these, so the surplus will go to state C, and C will receive the additional seat and be assigned 8 seats in Congress. Okay, so if we do that, that'll bring that total up to 30 seats. That's Hamilton's method. Now let's look at the quota rule. A group's apportionment should be either its upper quota or its lower quota. An apportionment method that guarantees that this will always occur is said to satisfy the quota rule. A group's final apportionment should either be the nearest upper or lower whole number of its standard quota. Okay, and we can see that in this case in Hamilton's method, the quota rule is met because C takes its upper quota, all the rest of the numbers take its lower quota. As long as we don't go over the lower or upper quota on any of the states, we're fine, and we can pass the quota rule. Let's look at Jefferson's method next. We want to find what we call a modified divisor, D, such that a group's modified quota is rounded down to the nearest whole number. The sum of the quotas is the number of items to be apportioned. The modified quotients that are rounded down are called the modified lower quotas. Apportionment to each group is modified lower quota. Okay, let's go through here and look at this new example. It says a rapid transit service operates 130 buses along 6 routes, A, B, C, D, E, and F. The number of buses assigned to each route is based on the average number of daily passengers per route. We want to use Jefferson's method with D equal to 486 to apportion the buses. So let's apportion here. If D equals 486, the table below illustrates Jefferson's method. Okay, so here's what we've got. We've got 4,600, or 4,360 passengers for route A. Our modified quota here is 8.97. Our modified lower quota is 8, and our final apportionment is 8. Okay. If we go through with B, we have 5,130. Our modified quota is 10.56, and our modified lower quota is 10, which gives a final apportionment of 10. You're like, okay, you can work through all these numbers, right? So the modified quota is just the number of passengers in this case over that 486 that we set for our D here. Okay? So that's all we're doing. We're taking the passengers for each route dividing by 486. That's going to give us our modified quota, and we're going to round that modified quota down to get the modified lower quota. That's why even though 8 is at 8.97 here, we're still rounding it down because it did not reach the 9. Okay? So we're rounding down. Rounding each modified quota down to the nearest whole number, the sum 130 indicates that there are no surplus buses to assign. Okay? Because we wanted it to add up to 130. That is using Jefferson's method. Okay? So he came up with a modified divisor, D, such that each group's modified quota is rounded down to the nearest whole number, and the sum of the quotas is the number of items to be apportioned. So one of the things with Jefferson's method is that that modified divisor right there is going to have to work so that we don't have to do any adjusting after we round down. Like in that initial method, we had to add one here or add one there. And this one, it has to add up to that 130 or whatever number it may be in each individual case so that we don't have to add any additional seats or passengers or anything like that. Okay, let's look at Adams' method though. Adams' method says to find a modified divisor D such that when each group's modified quota is rounded up to the nearest whole number, the sum of the quotas is the number of items to be apportioned. The modified quotients that are rounded up are called modified upper quotas. The apportionment to each group is its modified upper quota. Okay, so looking at this same transit service problem where we have 130 buses along 6 routes, A, B, C, D, E, and F, the number of buses assigned to each route is based on the average number of daily passengers per route. We want to use Adams' method to apportion the buses. Very similar looking chart here. Okay. What you'll have to do here to find this modified divisor is you will have to do some guesswork. Okay. The closer you can guess after going through this, the better, right? We're going to guess for this one about 512, okay? So originally we were going for the lower quota with Jefferson's method, and we used 486, but we want to go for the upper quota here and have it work, so we got to go a little bit bigger on the divisor D. So I'm going to guess and start out with 512, okay? Then we're going to go through and we're going to find this modified quota by dividing the number of passengers by this 512 that we kind of just guessed at. Okay, so we're doing 4,360 divided by 512 gives us 8.52. The 5,130 divided by 512 gives us the 10.02, and so on through the list. Now, we're going to round each of these numbers up using Adams' method. So the 8.52 goes to 9, the 10.02 goes to 11, the 13.83 goes to 14, the 20.01 goes to 21, the 30.34 goes to 31, and the 44.24 goes to 45. So we're rounding them up regardless. Even if it's really, like if you look at the 10.02, that is definitely closer to 10 than it is to 11, but regardless, we're still rounding it up to 11. The problem that we have here with what we guessed, we just took a random stab at it with this 512. The problem is when we took that guess, we were a little off. We added up to 131, but the sum should be 130. What that means is we're going to have to adjust our divisor a little bit. So, because the sum of the modified quotas is too high, we need to lower the modified quotas. Okay? In order to do this, we need to try a higher divisor. If we let D equal 513, we obtain 129 for the sum of the modified quotas. So, what we see here is if we move to 513 from 512, because we just tried 512, If we move to 513, what happens is if you were to work through that table, you would wind up with 129. So with Adam's method here, what I'm showing you in this example is that none of the whole numbers are going to work. Okay. So what we actually have to do is find a modified divisor that is between 512 and 513. So because the sum is too low, we decided to increase the divisor just a tad bit to 512.7 instead. Okay, so this is what it comes out needing to be in order for this rounding to work correct. Okay. If I do the modified quota by dividing by the standard divisor here, or the modified divisor here, 512.7, what we see is we get a modified quota of 8.5, 10.01, 13.81, 19.98, 30.30, 44.18, which causes all these to round up. The 850 rounds up to 9. The 1001 still rounds up to 11, even though it's really, really close to 10. We're still rounding all of them up. 1381 goes up to 14, 1998 goes up to 20, 3030 goes up to 31, 4418 goes up to 45. If you add all those numbers together, we get what we wanted, which was the 130. So that final apportionment is going to work with Adam's method. Okay. Now, we got one more to go. We're going to look at Webster's method. We want to find a modified divisor D such that when each group's modified quota is rounded to the nearest whole number, the sum of the quotas is the number of items to be apportioned. The modified quotients that are rounded down are called the modified rounded quotas. Okay? Apportion to each group is modified rounded quota. All right. Same example, same transit example, same numbers here. We're going to use Webster's method, however, to apportion the buses in this case. So what we're going to do is we're going to begin by guessing at a possible modified divisor D that we will hope works. We're going to guess 502. Okay, a divisor greater than the standard divisor, which we initially set at 500. What we would attain is 129 for the sum of the modified rounded quotas. Because 129 is too low, this suggests that D is too large. So we guess a lower D, say D equals 498. So sometimes it's hard to tell which direction you go. So you have to do a little bit of guessing at these modified divisors. You might go a little too high, so you have to go a little bit lower. Okay, so the D that's going to work here for us is actually going to be 498. Because in real life, they don't give you the numbers for these. You kind of got to work at them. Okay, so that's essentially what we're kind of working through here in this initial example. So if we look at this and I divide by the 498, what we see here is that 4,360 divided by 498 gives us a modified quota of 8.76, which we round up to 9. Okay. Then 5,130 gives us a 10.3, which we round down to 10. Okay. So we're rounding this one to the nearest number. We're not rounding up. We're not rounding down. We're rounding it to the nearest number for Webster's. Okay. So the 8.76 goes up to 9. The 10.30 goes down to 10. Okay. Remember, your threshold for rounding up and down in a standard case is 5. At 5, we round up. At 4, we round down. Okay. So we're looking at 1422. That rounds down to 14. 20.57. That rounds up to 21. 31.19 rounds down to 31. And 45.48 rounds down to 45. If we add all those together, we get the 130 that we want, so that our final apportionment is the modified rounded quotas for the Webster problem, or the Webster method in this case. Okay, so there's a few different methods that we can go through and use to figure out what to apportion where. And apportionment can become very, very important because, like I said, especially when it comes to Congress and you want to apportion so many seats based on certain things, you don't want to over apportion or under apportion individual scenarios. So this completes chapter 13.3, and I will see y'all next time.